Hello everyone, this is chapter 3.4, which will discuss the chain rule. Now before I specifically say what the chain rule is, I want to do some examples to take note of something specific, then we'll get into actually what the chain rule is and then observe some very useful consequences of that. So here, to take the derivative the way we're used to, we have to expand this out first, so I'll kind of just do this for you and just take my word for it that it works. Or if you like, you can, this should be a 12. Or if you like, you could actually do it out. Just x plus 2 multiplied by itself 3 times and you'll get this. Its derivative then is, let's see, it's 3x squared plus 18x plus 12. This factors, you can pull out a 3. And what you'll have left over is, actually, hold on, this is 12. My mistake. There's no 18, it's 12. So when you factor out the 3, let me write it here. You get x squared plus 4x plus 4, and this factors as x plus 2 all squared. So I'm going to write this as my answer. And what I want to notice for this example is if we treated the inside as x, then it's x to the third. Derivative of x to the third is 3x squared, and this is 3 times the original inside squared. So it seems like the power rule would work here. And that's kind of what the chain rule says to do. It basically says that you can apply whatever rule you need, leaving the inside the same, but actually it's not that nice in general. This was easy to see, but there's something specific that we're not quite seeing here because of the inside being of a certain form. Here the inside has a different form. Okay, so now for the second one, I'm going to try to notice something kind of similar. We're going to handle it in the same way. So let me just kind of explain that if you FOIL this out, notice since they both have x in common on the inside and it's to the third, really you can pull out x to the third out of this quantity and you'll have x plus 2 to the third, which is just that. So really this will get x cubed times this, and if you distribute that in, you just basically add 3 to each power. So you end up getting that. Now, once you take the derivative of this, term by term, what do we get? We get 6x to the 5th plus 30x to the 4th plus 48x to the 3rd plus 24x squared. Now, you could try to follow a few ways of factoring this, but I don't want it to take too long. So what I'm just going to show you is a special way of factoring this, which will look kind of weird, but I'll explain why it's true. So if you actually factor by pulling out 6x squared, and then go from there, you'll get a 4-term polynomial that's hard to factor. But in actuality, this can be factored as the following. 3 times x squared plus 2x to the second times 2x plus 2. And of course, if you pull 2 out from this and multiply it to 3, you get that 6, and you can pull out x from this into the square to get that 6x squared. So that polynomial, after pulling out 6x squared, should factor as x plus 2 squared times x plus 1. But again, you can try that on your own to figure that out. Now, I wanted to leave this as my answer, and I want to note something similar to what I noted for the first example. And that is, had we apply the power rule, it would be 3 times the inside quantity squared. If you do that here, you get 3 times the inside quantity squared. So that's true for this, but then where does this factor come from? Well, this in essence is explaining really what the chain rule says. This quantity here is just the derivative of the inside. So notice derivative of x squared plus 2x is indeed 2x plus 2. Now what about here? Well, what was the derivative of the inside here? Derivative of the inside is just 1, and multiplying by 1 doesn't do anything. So in fact, that property is actually true here. So now I'm going to describe this phenomenon in a more general way. Right, so here formally is the chain rule, and it says if capital F of x is the composition of two functions f and g, which is just one function of another function, so f of g of x, then capital F prime of x is f prime evaluated at the original g of x multiplied by the derivative of g prime after that. So basically you take derivative of the outside function f, keep the inside the same, and then take derivative of the inside after the fact, which is actually what we kind of did in the previous two, and we'll do in this example shortly. But first let me say that in Leibniz notation, if you remember the dy over dx notation, if we let f of u be y, and where u is g of x, so basically what we're doing is we're calling this inside u, and then we can say if f of u is y, and u is obviously g of x, then dy over dx is just dy over du times du over dx. Now notice dy over du is the derivative of y with respect to the variable u. So that's just f prime of u. So yeah, that's just the derivative of f, leaving the inside the same. Multiplied by u prime of x, that's the derivative of the inside. That's the derivative of u with respect to the variable x. Now the really nice thing about Leibniz notation is it looks like, well, since the notation here looks like fractions, it looks like the du's cancel. And there's actually a really nice way to prove the chain rule using essentially Leibniz notation with the fact that the derivative of y with respect to x, by definition, is equal to the limit as delta x approaches 0 of delta y over delta x. Now this is a strange way of writing that we haven't really done, but this essentially is definition of derivative. Only instead of using f and x and h, we're using the change in y's, which is f of x plus h minus f of x. And then instead of h, we're using delta x. So it's really the same thing though. It just looks kind of different. And the nice thing is it kind of tells us where this Leibniz notation comes from. Notice d here kind of stands for delta. So yeah, it's in the book on page 199. It may be different depending what version of the book you're using. But yeah, if you just kind of follow through the steps there, you can actually prove the chain rule. I'm not going to do that, but I'm at least going to show that in Leibniz notation, it looks like these cancel. So that's kind of what happens. If you multiply top and bottom by delta u, which is this represents as du basically, you end up getting this similar form. There's some rigor that I'm leaving out, but that's basically the proof. But in any event, let's just continue and move on with this example here. So if we can follow these steps correctly, basically what we want to do is we want to call the inside u. This is a fine way of getting used to the chain rule. So what we're establishing is that u is equal to x squared minus 3x. And we want to find, well, g prime of x, which you can think of as u prime. So u prime is the derivative of, well, u with respect to x. So think of u prime as du over dx. So that's just, in this case, 2x minus 3. So that's the derivative of the inside. The outside function, that's sine of u. So what's the derivative of sine of u with respect to u? That's dy over du. That will be cosine of u. So we can say that this derivative, f prime of x, according to the chain rule, is derivative of sine, which is cosine, of the original function u, which I'll write it as x squared minus 3x, but then multiplied by u prime, which is 2x minus 3. And for this particular case, I want to rearrange these terms because very often people can get confused and think that these quantities actually multiply, and they don't, because this quantity is inside of cosine, where this quantity is multiplied to that whole thing here. So this doesn't interact with the argument of any trig function. So for that reason, I'll write it in front just to avoid that ambiguity. And that, I think, is one of the biggest problems with the formatting of the chain rule, that we very often pull derivatives of the inside out on the right, when in most cases we should write them on the left. But it's just the way we're kind of set in our ways as far as writing equality and then starting with it and then doing that sort of motion. So for that reason, I very often rearrange, and we'll see a lot of that in this section. So I'm going to do a few more examples, and I'm going to show you some consequences. All right, so now for these three examples, we're going to be, of course, applying the chain rule. For the first one, well, notice for derivatives, we don't like radicals. Instead, we like 1/2 powers. So I'm going to replace, I should say, the radical with 1/2 power. And then, by chain rule, I'm going to treat the inside as u, take the derivative with respect to u. So imagine you're covering this, think of it as u, or x, I guess. Derivative of x to the 1/2 is 1/2 x to the negative 1/2, or u. So the original inside, basically. So it's x squared minus 6. And then by chain rule, you multiply by what? By the derivative of the inside. Derivative of x squared minus 6 is just 2x. And notice in this case, we have cancellation of 2's, here and here. And since it's negative 1/2 power, well, since the power is negative, it's really in the denominator, and 1/2 means radical. So we actually have this as a radical in the denominator. So in total, we have f prime of x is equal to x, this term, over the square root of x squared minus 6. Perfect. Great. Now for the next one, it's a little different because the inside is the power here. So there's no actual parentheses to signify an inside like there were in all of the previous problems we've seen. Instead, we have a power as being our inside. But again, if we treat it as u, derivative of e to the u is itself. It's e to the u. So this is e to the original inside, and then by chain rule, multiply by the derivative of that inside, cosine of x. And that's it. I'm not going to rearrange anything here. You could, if you want, you could write cosine in front of e to the sine of x, but this is okay. All right. Now this one is, well, it's a little involved because there's actually a function of a function of a function. So there are 3 functions here. And this is actually the main reason why I believe it's called a chain rule, because we're taking, we're taking chains of derivatives, basically. Derivative of the inside, and we keep doing that until we run out of the insides. So here. So first we're going to start with the outermost function, which is tangent. Derivative of tangent is secant squared of the original inside, e to the x squared, times derivative of that inside. So it's almost like we started here, and now we're on this layer. Derivative of e to the something is itself, so it's e to the x squared. And then multiply this to the derivative of that inside, which now we're on the 3rd layer finally. And derivative of x squared is 2x. And there we go, that has no inside actually. In fact, if you think the inside is just x itself, derivative of x is 1, and you stop there. But in reality, we just stop once we have no more insides, and this is it. And we could rearrange this by writing 2x in front. In fact, let me do that just so we get used to it. So I'm going to write my final answer here as f prime of x equals 2x e to the x squared secant squared of e to the x squared. Which I know looks a little goofy, but believe it or not, that's how you find derivatives with these sorts of things. Great. So now I'm going to show you some very nice consequences that are basically generalizations of all the examples we've seen so far, and then we'll see something a little new. Alright, so here are the consequences of the chain rule that I was speaking of earlier. So we have one, of course, for the power rule, for sine and cosine, and for e to the something. Now, I could have written more. Like there's obviously one for every trig function as a consequence as well. In fact, from the previous example we saw one for a tangent, and that of course is just, its derivative is just secant squared of the inside multiplied by derivative of that inside. So here we kind of see more or less what's happening, but specifically with a certain outside function. So here the outside function is power, here it's sine, here it's cosine, here it's e to that. So all we're doing again is just applying those normal rules, but then multiplying by derivative of the inside. So really it's just a special case of the chain rule. And we'll see that here for cosine squared. But the thing to realize though is cosine squared, what cosine squared of x means, and same thing for sine squared and tangent squared and all of those, really is cosine of x all squared. Sometimes the parentheses are omitted here and here on the inside, so just cosine x means cosine of x. But anyways, this is a power rule chain rule. So derivative of u to the second is 2u. So it's 2 times the inside, cosine of x. Multiplied by derivative of the inside, which is negative sine. And just so I don't have to rearrange too much, let me write sine and make the answer negative. So this will be f prime of x. So yeah, after getting used to the chain rule a little bit, these problems basically just become one-liners. And now we're going to see something a little new. These consequences are kind of just specific versions of the chain rule depending on what the outside function is, like I said earlier. But what we're going to see now is something a little different. So let's take a look. Alright, so here finally is the general exponential rule, which is the new thing we're learning in 3.4. And of course I'll be proving this by the chain rule, using the chain rule, and some logarithm properties that I've written here that I'll shout out as we go along. But let me just kind of observe and say what this says. So it says the derivative of some number to the power x, so here a is just a constant, is itself a to the x, but times ln of the base a. So here a is a positive number, not equal to 1, because of course 1 to the x is just 1, and derivative of 1 is, well, 0. Which, by the way, also kind of works, but we're just assuming a is a positive constant. In any case, the first thing I want to do to prove this is I'm going to write a to the x as e to the, well, ln of a to the x. And that's just using, I guess, this property here, the third property I've written. E to the ln of x is just x because the e and ln's cancel. If we bring this power x out using this power rule of logarithms, which is the last thing I wrote here, is e to the x times ln of a. And remember, since a is just a number, ln of a is also just a number. Okay. The derivative of this, so let's write an arrow for d over dx, is itself, because derivative of ln of something is itself, times the derivative of the inside because of chain rule. And what is the derivative of the inside? Well, the inside is just the power here. The power is a number times x. Derivative of a number times x is just that number. In this case, is ln of a. Perfect. And now what? Well, we know this quantity here is just the same as a to the x. So finally we get a to the x times ln of a, and that ends the proof. Now, one thing I wanted to also say is that this is the general exponential rule. So if you think of the natural exponential rule, e to the x goes to itself. When a is equal to e in this case, you get derivative of e to the x is itself e to the x, but times ln of e. But I've written here ln of e is 1. And in fact, that's true for any base. So remember, ln means log base e. But if it was log base 3 of that base 3, it's also equal to 1. So these properties are just kind of natural log versions of more general logarithm properties for any particular base. So now let's move on to some examples. So here we want to find y prime. So for the first one, we're just applying the rule we just found out. So y prime is equal to, in fact, let me use a Leibniz notation, dy over dx is equal to itself times ln of the base. And sometimes we don't need to write parentheses, so I'm just writing ln of 3 just to exercise that. But there it is. For this one, it's very similar. Let's see. So its derivative is using that rule above itself times ln of the base times derivative of the inside. Okay, so now what is the derivative of the inside? Derivative of the power, this is our inside, is, well, 2x minus 3. And you can write that in whichever order you'd like, but I'm just going to leave it like this. And there we go. That was 3.4. So we saw the chain rule. We saw some good exercises and examples involving the chain rule. We saw some nice consequences that basically what happens when you combine the chain rule with other previous rules that we've learned. And then finally, a nice consequence of the chain rule is a new general exponential rule, where the base is any base that's not just e, like 3 to the x, for instance. Great. So I hope you enjoyed. I'll see you in the next videos for 3.5 and 3.6. See you then. Thanks for watching.